We are live. Okay. The under desk. Right here. Too bad. Turn. Now. Okay. So you couldn't possibly do the first do it question because I didn't draw a picture for you. And you could have done B and C on this one, but I didn't draw a picture for A. Bad me. Yo muy malo. Now what I'm going to do, Anthony, if you're going to continue to turn around, you're not going to possibly do. Now, I'm going to draw a line for A, and then you figure out which one has the greatest rate of change.
Is it actually killer hard?
No, I think it's killer easy.
But why'd you put killer hard?
The one before that was killer hard.
What? What is it? Never mind.
Okay, so find the rate of change for each of these problems and mark down which one you think has the greatest rate of change. Okay, what's the rate of change for A? 3 over 2. Good, right? Because we go up 3 over 2. What's another word for rate of change? Slope. Excellent. What about B? What's the rate of change for B? 5 over 2. Excellent. What's the rate of change for C? What am I going up by here?
3.
4. What am I going up by here? So what's the rate of change? 4 over 1. Which is bigger, 3 over 2, 5 over 2, or 4 over 1? 4 over 1. Not even close.
Small but closer to 1.
Well, the easiest way to do it is to use your calculator. Everybody do 3 divided by 2.
That would make a lot of sense.
What is 3 divided by 2? 1.5. Let's do 5 divided by 2. 2.5. So far B is biggest. Let's do 4 divided by 1. 4. What's the biggest one? 4. So the greatest rate of change is C. Does that make sense, everybody?
Yeah.
Okay.
Oh, yes it does.
Yeah. Just tiny bit. No.
Michael, can you kill the lights, please? Today, we shift gears.
Shift to what?
And so far we've learned littlest to biggest, littlest to big. And we've learned Pythagorean theorem. Now we're going to take those two concepts and we're going to begin to apply them. We're going to begin to apply them in the world of transformations. Now there's lots of transformations. You guys have seen the movie Transformers?
Yeah.
Okay. Calm down about Megan Fox. Okay. Now, they took like a thing like a car and turned it into Megatron or something like that.
Oh, mechanoid.
Meganoid, whatever it is. I didn't really watch the movies. Okay. Now, the bottom line is, to transform is to change. To become something that is different in nature. So, we have several different types of transformations. We have reflections, we have rotations, we have translations, we have glide reflections. We also have a thing called the dilation. And today we talk about dilations, okay? Now, in the English language, we would often use the term dilate when we talk about our eyes. My wife, she just had LASIK surgery the other day, And as part of that process leading up to the actual surgery, they dilate your eyes. Have you ever had that done at the doctor's office, right? Where they put the drops in your eyes and it makes your eyes go really wide so the doc can see what's going on inside your eyeball?
No.
Well, another time where your pupils could be dilated is when you go from dark to light. A classic example is in the wintertime when it snows and then the next morning it's bright sun and you walk outside the front door and the brightness of the snow hits you and it almost like causes a headache, right? Like, whoa!
You just close your eyes and you gotta
Yeah.
refresh.
Now, and you might even like open them like looking at the ground like this and
That's
slowly
I
work them
always
out.
do that.
That's because your pupils have dilated. It means your pupils smaller, everything stays proportional. Everything stays proportional. That means little is to big is little is to big. Now, stop. Now, have you all, I'll give you a good example of this. Have you all seen the movie Beetlejuice? Okay. The very last scene in that movie is Michael Keaton, who stars as Beetlejuice, sitting in the waiting room, and next to him is this guy that looks like he's on steroids. He's got the most massive chest, shoulders, arms like foundries, legs, hips, body, everything is huge except a little tiny head. And if I remember right, about like that, right? Yeah. Right?
What?
Now, it's a little tiny head. That's not proportional. If the whole body gets bigger, what's supposed to get bigger too?
The head.
The head. Now, another example of this, I think I mentioned this a couple of weeks ago, I started doing little is to big is little is to big, was the show Super Friends.
What is that?
I didn't watch cartoons much as a little kid growing up, but there was this one cartoon that I saw about 4 times. And it seemed that every time it was the same episode. And going back when my own kids were young, they were watching cartoons and I walked in and Super Friends was on. And it was the same episode. I have to wonder if they only made one episode of Super Friends. Now, Super Friends were about these 2 twins, a boy and a girl. And they had these rings, and they'd say, Wonder Twins Unite, and they would put the rings together.
I know. I remember.
When they would put the rings together, it would call in the superheroes. Batman, Aquaman, Superman,
Yep.
Captain
Okay,
Planet.
I know what
All,
you're
all of
talking
those guys, would come charging in to save the day. Well, the one episode that I ever saw was where there was an evil mad scientist. Don't cartoons always have evil mad scientists?
Well, not
And they always do on Scooby-Doo anyway. So, lo and behold, with the evil mad scientist, he calls all the Super Friends into some like container that was disguised, and he turns on the incredible shrinking machine. And they all shrink down to be super tiny versions of themselves.
Honey, I Shrunk.
But they still look like, yeah, like Honey, I Shrunk the Kids or Honey, I Blew Up the Kids. They still look like versions of themselves. Then, a little later in the show, of course, the Super Friends trick the mad scientist. The mad scientist goes into it, they shrink him down, and they go in and they reverse it, and they get back to normal size.
Can we watch this one day?
No, I don't think so. Anyway, dilations do this. They expand and they shrink in proportion. Another example might be, did you guys ever do models? Like you make a model, like a boat model or a car model or a plane model? Everything is proportional. They've got it all so it's in the same. You don't like keep the same size wings and change the body of the plane. Well, the boat doesn't keep the same size engine and we shrink the boat. That would sink the boat. Yeah, well, you got to keep everything proportional. So let's give you an example. Let's give you an example of that. And let's start by drawing this triangle ABC. Go ahead, draw it on your paper. Shh. Guys, if you're going to be distracted, you're going to learn less effectively. God bless. Okay, so A is the point 0, 0. B is the point 3, 4. 3, 4. So A, B, and C is the point 3, 0. So I can put them all together and I can form my triangle. Okay? And then it says we're going to dilate this by a scale factor of 2. Now I know that's a mouthful. It's a big long set of words. Now the thing is that to dilate is to make bigger proportionally. And to do that we need to multiply by the same thing, or possibly divide if it was make it smaller. But in this case we're going to, scale factor of 2 is going to make it bigger, so we have to multiply. So I'm going to find A prime, B prime, and C prime. Now we call this A prime, B prime, and C prime with these little marks because it means that like A is connected to A prime, B is connected to B prime, and so on. Yes?
Can there be E prime?
If there was A, B, C, D, E,
Alright.
but what you can also do is get double prime if I did another thing to it, or triple prime. Okay? Now, if I'm dilating, it means usually to multiply. It could mean divide. Everybody say dilate usually means multiply, could be divide.
I can't.
Okay, the only reason you would ever divide is if it was like a fraction, to make it smaller, like it was dilate by a half. That would be like multiplying by a half, which is the same thing as dividing by 2. So that's why it can be division. Now, I'm going to dilate by a factor of 2, which means multiply by 2. So what's 0, 0 times 2? 0, 0.
Oh.
What's 3, 4 times 2? 6, 8. Good. What's 3, 0 times 2?
6, 0.
Nice. So that creates for me the new triangle A prime, B prime, C prime. And let's plot those points. A prime is here, same point, didn't move. B prime though is 6, 8. So that would be 4, 5, 6, 2, 4, 6, 8. And C prime is another 3 there. So there it is. Now, can we see that the red triangle has the same shape as the blue triangle?
Yes.
And it's even more than just being triangles. Like, they both have right angles here. This angle is in both the red and the blue triangle, so obviously it's equal. And it's also true that the angle at B is the same as the angle at B prime. So that's how the triangles are similar. Remember, similar means same shape, sides proportional, different lengths in the sides. And that's exactly what we have going on there. Now, what do you notice about the size of these two triangles? Brendan?
A, B, C prime is twice as big as A, B, and C.
If we look at it in terms of length, that's true. Area, it's actually 4 times as big, but in terms of length, it is twice as big. That's well said. The most obvious conclusion is that they're different sizes. And then we can get a little more specific and say that all the lengths are twice as big. And I'll show you how we could do that. How far is it from here to here in the red triangle? 3, just count. How far is it from here to here in the red triangle? 4. Now, let's take a look at the blue triangle. How long from here to here? 6. And that makes sense, right? Because we've dilated by 2, which means multiply by 2. What's 3 times 2? 6. So this is 4. What would you predict the B prime, C prime length to be? 8. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yes, very good. So that works out to be 8 also. Now, those are the legs of the triangles. Now let's talk about the hypotenuse from here to here. Now, does everybody see the right triangle in red?
Yes.
What law or theorem could you always use in a right triangle?
Pythagorean.
Pythagorean theorem, very good. So what does the Pythagorean theorem say, everybody?
Leg squared plus leg squared.
That's right, very good. So, and I'm just going to use an H for hypotenuse. Is this 3 a leg or is it the hypotenuse? Leg. Brian, head in the game. Is this 4 a leg or the hypotenuse? Leg. So I'm going to get 3 squared plus 4 squared is H squared. Finish it up. Okay. So what's 3 squared? 9. What's 4 squared?
16.
And that's going to equal hypotenuse squared. Same side?
Same operation.
9 and 16 is 25 is h squared. Square root, which is kind of a new step for us. H is, what's the square root of 25? 5.
7.
Very good. Now, you know how the blue guy is twice as big as the red guy? So the red guy is 5. Let's predict what the blue guy should be. 10. Well, let's go through and see. Once again, leg squared plus leg squared is hypotenuse squared. What's the first blue leg? 6. 6 squared. Plus, what's the second blue leg? 8 squared equals h squared. Go ahead, figure it out. We all get 10?
Yeah.
Right? Because the square root of 100 is 10? Good, and that makes sense now, because this side is 5, and this side is 10, and that again is twice as big. Okay, dilate means multiply. Now, very important consideration here. Excuse me. Now, is there a reason why people are packing up and we got a couple minutes to go?
We have 2.
Math people are brilliant and lazy. And in the last problem, we wrote out this big long sentence that said, we want you to dilate by a scale factor of 2. Could you imagine if every time we wanted to ask a question, we had to say or write that? That'd be a lot of work. But look over here. This means, see here, let's dilate by a scale factor of 5. That means multiply by 5, I get negative 15. We could stay after the bell if you wish. Eric, let's not talk. I could write that out every time, but this means the same thing. What do you think the D stands for?
Dilate.
Dilation. Hold it. What do you think the 2 stands for? Multiply by 2. 8. 18. Okay? Hasta la vista. Vaya con Dios. Toodaloo. Ta-ta. Arrivederci. Smile a lot. Ciao. Arrivederci. Adios, amigos y amigas. Garusharus. Gadafis. Shalom. Sayonara. Hasta la bye-bye.